Okay, so we know about the disk method for finding the volume of a solid with using integrals. Now we're going to use the washer method, and the washer method would be when we have something like this picture right here. So if you look at this picture, it's got an area that is bounded on top and bounded on bottom. So when we actually rotate this area around the x-axis, you see as it comes out, it builds up and it builds this 3D shape, which is pretty cool. But you see the 3D shape actually has a hole in the middle because the original curve, the original area doesn't actually touch where we rotate around. So it's going to end up with a hole in the middle. So when we have a hole like this, we're going to have to use something called the washer method. So let's take a look at how that actually works. So we have these examples. Let's just start with this first one. So this one is a disk method, and the reason that I know this is a disk and the other two are washers is not just because it says it on my paper, but the disk method, if you look at the disk, see how this curve is touching where we're going to rotate around, right? So we're rotating around this line, and the curve goes all the way down to it. So our region is going to touch all the way around. But if you look at something like this, here's our curve, here's our area, and we're going to rotate this around, but we're going to rotate it all the way down here. And you see this entire space in between, right there, you see all that space in between? That's going to create a hole. So this is how I know I need to use the washer method. So let's review the disk method really quick. The disk method says that the volume of a solid equals pi times the integral from a to b of the radius squared of the disk that we form. And so then we have to figure out what the radius of this disk is. And remember, the radius is the space, the distance from the top curve to the bottom curve. So we're going to take the top curve minus the bottom curve, which is 0. So our radius is negative x squared plus x. So the volume of this solid is going to be pi from a to b of negative x squared plus x dx. And then the question is, what are our limits of integration? Let's figure out where this curve crosses the x-axis. So, you could either set the two functions equal to each other, so negative x squared plus x equals 0, or you could just find the zeros of this function because this one happens, where it crosses y equals 0 is 0. But we'll just remind ourselves how to do that. So we want to find where these intersect. So we're going to take the first function and set it equal to the second function. So we have negative x squared plus x equals 0. And we're going to factor out the x, and we're going to get a negative x plus 1 equals 0. And then we decide, when does this equal 0? Well, when x equals 0, that would be true, and also when x equals 1. Which means these curves intersect when x equals 0 and when x equals 1. So our limits of integration are going to be 0 and 1. And that's the end of that. So this is the volume of a solid that's revolved around the x-axis. Now, this next one, like I said, you're going to look at it and see that it's going to revolve around a different line. So it's going to do a revolution around this line, y equals negative 1. So for the washer method, our formula, you can find it up here, our formula is volume equals the integral from a to b of, I forgot the pi. You can put the pi on the inside too, but pi times the integral from a to b of r squared minus little r, big R minus little r dx. Okay. So what's big R? What's little r? How are we going to do this? So let's very first, we realize the limits of integration are going to be the same for this second function. So we can start writing our integral. It's going to be volume equals pi times the integral from 0 to 1 of big R squared minus little r squared dx. And then we have to figure out what little r and big R are. And so we look at the big R, and you can't see it very well on mine, but I think you can see it on your paper pretty well, is this space from the top curve all the way down to the axis of revolution. Okay, so we're going to take the top curve all the way down to the axis of revolution. And so it's going to be, remember to find the space in between two curves is top curve minus bottom curve. So big R equals, and make sure as you're writing this that you write big R equals instead of just like a lot of random calculations, because then it helps someone else reading your test or your work understand what your thinking was. So big R equals our top curve, which is negative x squared plus x, minus our bottom curve, which is negative 1. So big R equals negative x squared plus x plus 1. And then little r is going to be this area in between the bottom of the function and our axis of revolution. So it's just from the bottom to the axis of revolution. So how far is it from the x-axis down to negative 1? Well, it's 1. How far is that? It's 1. And so you could do, again, top curve minus bottom curve. So top minus bottom. And the top curve is y equals 0 minus the bottom curve, which is y equals negative 1. So little r equals 1. So we can just go ahead and replace, in this function, we can replace big R with what we just found big R to be, and little r with what we found little r to be. So our final answer is going to be that the volume of this solid is going to be pi times the integral from 0 to 1 of negative x squared plus x plus 1 squared minus 1 squared dx. So if we evaluated that, we would find the volume of this solid. Okay, the last one we're going to look at is this one. We're going to rotate it around one that's above it. So it's just a little bit more challenging to picture. I'm going to go ahead and do it a little bit of erasing here so that we have plenty of space. Okay, so let's picture this one. Again, our formula stays the same. We just have to figure out what big R is and what little r is. So big R is going to be from our axis of revolution, which is right here, all the way to the farthest point on our solid, or on our area. So it's going to go all the way down to there. Do you see why it goes all the way down there? Because we're going to get from our axis of revolution all the way to the farthest point on our region, so that makes that big R. And then little r is the space in between the axis of revolution and the closest point on our curve, so that's little r. And so if we want to figure out what the little r and big R here are, little r and big R are, I keep saying that and I feel like a pirate. So big R equals top curve, which is 2, minus the bottom curve, which is 0. So big R equals 2. And then little r, okay, just making sure. For a minute, I glanced at another one. It said big R is 4, and I wrote that in my own handwriting. I was like, what? That's not it. Okay, little r is the top curve minus bottom curve. So little r is 2 minus, and the bottom curve is negative x squared minus, or plus x. So little r is 2 plus x squared minus x. And so then we just plug that into our function. So our final function is volume equals pi times the integral from 0 to 1 of 4 minus 2 plus x squared minus x squared dx. Okay, let's look at a couple more. So we're just going to set up the integrals for these volumes. So we're going to rotate this about the x-axis again. And so we have our integral of volume equals pi times the integral from a to b of big R squared minus little r squared dx. So Let's find big R and little r on here. Okay, so big R is going to be from our axis of revolution, which is the x-axis right here, from our axis of revolution to the farthest away point on our region. So this is R right here. And then little r is going to be from our axis of revolution to the closest point on our region, which is right there. So big R equals top curve minus bottom curve. So top curve minus bottom curve. So this is going to be, let's see, our x plus 2. I have to remember which one. Well, they're right in front of me. That one says x plus 2. So top curve minus bottom curve is 0. So big R is x plus 2. And then little r is top curve minus bottom curve. That's what we're trying to find, is the distance, right? And so that's x squared minus 0. So that will be our big R and little r. Oh, and then we need to find our limits of integration, right? We need to figure out where do these two intersect. So we set them equal to each other. We say, when does x squared equal x plus 2 to find our points of intersection? So that's x squared minus 2 equals 0. And that factors to x minus 2 and x plus 1. That means that they intersect when x equals 2 and when x equals negative 1. So there and there. So our final integral on this one, I should have left myself more room. The volume equals the integral from negative 1 to 2 of, man, there really is no room here. I'm just going to have to erase all of this. I just have to remember it. Okay. Volume equals pi times the integral from negative 1 to 2 of x plus 2 squared, which is big R, minus x squared squared, which is little r, dx. So that's the volume of that washer, or of that solid made by washers. Okay, last one. Set up the integral, and it's going to go about the line y equals 4. So our line of axis of revolution is up here. So we got to define big R and little r. So big R is going to be from the farthest away point on our function, like the farthest function away, all the way to the axis of revolution. So that's going to be big R. And then little r, let me do that in the right color. That's going to be big R. And then little r is going to be from the axis of revolution down to the closest function. Okay, so let's find these. Big R is top curve minus bottom curve, so that's 4 minus x squared. And little r is 4 minus x plus 2. Remember, we're subtracting the whole function. So little r ends up being 4 minus x minus 2, which is 2 minus x. Okay, so then if we want to write our actual volume equation, we're going to have volume equals pi times the integral from negative 1 to 2, because those are still our x values that we're using, of 4 minus x squared minus 2 minus x squared dx. That's really messy. I apologize for that, but I ran out of space. So this is going to be our integral for this one. So we'll take a look at some more conceptual stuff hopefully in class. I might make an extra video that's optional if you'd like to just see the concepts behind it, but hopefully you have now the process.